So, good afternoon everyone. My name is Marito and I'm here to present a paper on unified algorithmic framework for block structure optimization involving big data with applications in machine learning and signal processing. These are the authors of the paper and it was published in 2016 in Signal Processing magazine. So here's a brief outline of the presentation. I'll give you some introduction of the topic and why this is nice and desirable and we think it's important. Then I'll present some theoretical properties of the algorithmic solution. I'll show some algorithms covered by this framework and then I'll give some applications on machine learning for this technique. Then I'll conclude my presentation and at the end you can see some reference if you want to dive into the topic. So here I'll give some overview on big data. So big data is available in many areas: engineering, biological, social and physical sciences. And then we have many challenges involving big data. For instance, we have the size and complexity in the algorithm design. And then you also have the problem in implementing these solutions into the hardware and everything else. And a possible solution for these problems are what we call large-scale optimization. But then we can ask the question, why not just use the general purpose optimization that we just have? For instance, dual optimality and something like that. Why not? The problem is the complexity of the model. Then we have different types of data. And also, of course, the huge data size. And these problems are not optimized for any of these points. Then we have another question, how can we be efficient in these applications? For instance, each step should be simple and easy to perform. We want also that immediate results are easily stored, so that you don't use a lot of data just to save that. If possible, we need the algorithm solution to be distributed or parallel. And then you want high quality solutions with the small number of iterations. That's the dream goal. So this is the general problem formulation. And then we have already some algorithms that can satisfy most of these properties. For instance, the well-known block coordinate descent, or what is also called alternating optimization. And then here they presented the framework, the block successive upper bound minimization, BSUM. And here we have the general problem. Consider this block structure optimization, where we are trying to minimize an objective function with the variable x, and then we have any blocks. Each x is a vector which has any dimensions, and we are trying to optimize this function which is constrained into this set. And we assume that this set, the big set X, is the Cartesian product of all the other sets. So we have no constraint coupling these different sets. And that's a very important assumption. So here we assume that this function is continuous, can be non-convex or non-smooth, and the set is closed convex, the set X, which is within the reals.
Sorry, just one question. So these two algorithms were presented here for the first time, or there's a background?
No, the BSUM is presented here for the first time, but BCD is already well known.
Okay.
So here I'll give some basic steps of the BCD method, which is already well known. The idea is to partition the optimization problem into any blocks, one for each variable. And then we optimize each block per iteration, which means that in one iteration we find the minimum of this function while fulfilling my constraints. And then I do that in a cyclic manner. So I do for the first block, considering all the others fixed, for the second, considering all the others fixed, until I converge to my solution. And here we can see some example of that. We start here, and then we optimize over x1, we go here, now we optimize over x2, and then x1 again. And then we converge to this point. So that's the general idea of BCD. And then for BSUM, the objective is to optimize upper bounds of the original function in a block-by-block manner. But then we can think of this, why not just use BCD? First, if the function is non-convex, each subproblem may be difficult to solve exactly. And BCD has some constraints on it, not exactly constraints, but assumptions that you need to fulfill. And with BSUM, it may be easier for you to fulfill these assumptions. And BCD may not necessarily converge for these cases. And as we see here in the paper, BSUM is a big framework that can fit all these different classical statistics and machine learning algorithms. For instance, expectation maximization, the famous convex-concave procedure, block coordinate proximal gradient, non-negative matrix factorization, and many others. So now I'll present the algorithm itself, the assumptions, and the theoretical properties. So first we consider the upper bound function, ui, which is an approximated function of my objective for that variable xi, for each coordinate at a given feasible point z. And then I define a set IR, which is the set of indices that I will pick for these iterations. And then the idea is that at each iteration R, the BSUM method performs this update. I will minimize the upper bound function, not my objective function, over that interval, maintaining all the others fixed. So that's the general idea. And then until some convergence criteria is met. And for the convergence you can think of as the previous three successive iterations that is smaller than some background and some predefined epsilon. You can think of as the gradient should be smaller than something, so you can, that's also the freedom of you to decide the convergence criteria.
So basically here I think it's important to point out that BSUM is like kind of a generalization of BSUM.
Yeah, you can think of
So
it
instead of-
as the big umbrella that fits
Exactly.
all these other
Exactly.
solutions.
And instead of optimizing the function itself like BCD, you optimize
Yeah.
an upper bound.
You
actually.
optimize an upper bound. And then we see now how to get this upper bound and what are the desirable assumptions that you have for this upper bound. But the first question is how to select these indices. These indices here, they are IR. We have many selection rules. The first one and the easiest one and most popular is the cyclic. So we do this in the order of 1, 2, until n, and then we cycle back. But you can have many others. And you can see in this reference 1.4 many examples and convergence proofs for these orders. For instance, you have the randomized rule, and that you select randomly at each iteration which block you will optimize. You have the Gauss-Sauer, which is similar to some maximum improvement at each iteration, and you have many others. So now that, suppose that you have selected the indices, how to select the upper bound? That's a good question. Here in the figure we can see the objective function, f. Here we have some upper bound over this xir. And here we note that this function u is a global upper bound of f. It's not just an upper bound on this neighborhood of xir, and that's a very important assumption. And here we see that by using this upper bound we are going here on u.
And it should be convex for only a region or for the whole
You have different assumptions that you can, but generally what you want for this function u, you either want it to be strongly convex or convex with some other assumptions, or even pseudo-convex with some assumptions. But it depends on how you want to select this function and how your function f is also defined. So you have freedom on that. And here I present some examples of upper bound that you can use for some functions. But before doing that,
One question. You choose this function such that, I mean, you know where is the global optimum? You
No.
choose this function so
No.
that you go towards the, you don't know.
yeah, the
So how
idea
do
is
you
that
choose
you
it?
want to, I will talk that in some time now, but then the idea is that you want to go to the stationary solution. We cannot talk about global optimum because that's not defined. What you can guarantee is that you are going towards a stationary solution. And the goal is that this function, this upper bound function, has some properties that allow you to go to this stationary solution easier than the initial function, the objective function. And then based on the objective function that you have, you can select this upper bound in the better way.
And usually in these, I mean, for these optimization problem, in like trying to target trying to set a goal where you say, I want to prove global convergence, this is usually very hard actually.
Yes.
Yeah. Most of these problems are like entry hard. Yeah.
Yeah.
So I think at best you can show like locally optimal solutions or stationary points.
Yeah, that's the best that you can get.
Yeah.
So before going to the definition of stationary solutions, I need to define the directional derivative. So this is a generalization of the directional derivative that you have for smooth functions, because here we also allow for non-smooth functions. And the idea is that you want to find the lim inf of lambda of this function here as lambda goes to 0 in this direction d. So that's the general definition. And with this definition, we have some assumptions on the upper bound function. And what we call this set of assumptions, assumption A. So we want the function to be equal to my original function at the same point, x. Okay, so they should be equal at that point. We also want the function to be a global upper bound of f here. That's what A2 tells us, and that's a very important assumption. Depending on your objective, it may be very difficult for you to find some upper bound, some global upper bound, but it may be easier for you to find some upper bound on a very small neighborhood. And then you want them to have the same first order approximation, which means that the derivative of ui given at that point should be equal to the directional derivative of the initial function at that point. And then the function should be continuous. So this is the first set of assumptions on the upper bound. And given that, I have some examples of upper bound that you can select. The first one is what we call the proximal upper bound. You are given some constant gamma, and then you basically put the function, the initial function, and sum it with the proximal operator, gamma divided by 2. And why is this desirable? Because if the function is convex at this iteration and you include this proximal operator, then your upper bound is strongly convex and you have stronger convergence properties and maybe faster. And then if you also want to use some quadratic upper bound, suppose that you have the function as the sum of g and h, where g is smooth and has the defined Hessian, and then you can have this other upper bound, where you use g plus h, then you have the first order approximation of the function g, plus some term related to the Hessian of the initial function. And then you have many other approximation functions. You can have a linear upper bound, which is similar to Taylor approximation of the first order. You can have a Jensen upper bound, which is similar to the Jensen idea on the expectation of convex functions. And we have many others. And here on these papers, they present many others. One is the paper that I'm presenting, and 5 is another very nice paper on ICML. And they have many different functions and proofs related to the convergence and everything else. So if you want more functions, then you can check these references.
What is the z minus I here? What is the notation?
Okay,
Yeah.
so z minus I is to say that z minus I is all the other vectors fixed.
Right.
It's not for that
So this
iteration.
is z1 to zn excluding zi.
I. Yeah.
Okay, right.
Okay, so the next question is to understand when does this B sum converge. But before that, we need to have some definitions. The first one is of stationary solutions. So we say that a point x is a stationary solution of problem 1, which is the initial problem, if the directional derivative at that point is higher than 0 for all d, such that x plus d is within my constraint set. And you can think of this definition of stationary solution as the definition that you already know of stationary solutions in vector calculus. But this is more general for non-smooth optimization. And then you have the idea of coordinate-wise minimum solutions, which is basically the local minimum for a specific block. So you can think of stationary solution as some generalization or some better property than coordinate-wise minimum. But then you may ask, what if I have just a solution that is coordinate-wise minimal? Can I say that it's stationary? No, you cannot say that. In general, they are not. But we have the definition of regular points. And it's the point that if it's coordinate-wise minimal, then it's also a stationary point. And that's a very good property that you want. And many of the proofs on the functions and the assumptions that you have on the problem assume that the function is regular at all the points. And here we have some example of function that is all the points in the constraint set as regular. Is this function f such that it is the sum of g plus h. And h here can be a possibly non-smooth function, and it's divided in blocks already. This is a very famous approach, and many papers use that. Also in the classical idea of BCD. But here we are using that for the general upper bound function. And now I'll present the main result of the paper, which is the convergence of this solution. So first of all, we assume that we have a sequence generated by the algorithm. And suppose that assumption A holds, which are the assumptions on the upper bound function. And that each XR is regular. Then the following is true. A, we suppose that the function is quasi-convex in X high. And then you assume that for each subproblem, each block has a unique solution for any X arm in X. Then you can prove that every limit point of X converges to a stationary point. And here the critical assumptions are the quasi-convexity in UI, and that you need each block to have a unique solution. Then if you want to use different assumptions, we have B. Now you have an assumption that the constraint set is compact. And you assume that each block has a unique solution, but now for at least n-1 blocks. And then you can say that the sequence converges the set of stationary points. So these are the main results of the paper, and I'll give now some hints on the proof, because the proof is quite long, but not difficult, just long. So to prove part A, the basic idea is to use the quasi-convexity of the upper bound function to guarantee the existence of these limit points. And since we are solving a locally tight upper bound of the function f, the function is minimized at each iteration. So in the limit, this function converges to this fz, and z is a limit point. And then you use the idea that every subsequence converges to the point z, and you show that by showing by contradiction that this subsequence converges to z1, which is the coordinate-wise minimum of the big Z, right? But then since this function, the function and the points are regular, if you converge the coordinate-wise minimum of all of them, then this function is also stationary. And you do that by proving by contradiction. You assume that it's not, you have other minimums, and then you show that it's a contradiction. That's the general idea of part A. Part B, you use similar ideas, but now you don't have the quasi-convexity, and you allow for n-1 blocks to have a unique solution. But then you use the idea of compact set instead of the quasi-convexity to ensure that you have the function converging within the interval, or the set. And then the ideas are a bit similar, but the proofs are still long. I'm not presenting here, but it's in the second paper. Because here this paper is more general for signal processing people. And this reference 2 is the science paper, which they dive way more into the maths and the proofs, and it's a very, very nice paper. So now we have the question. We know that this framework converges, but then how fast does it converge? We have some other assumptions to ensure the convergence, to ensure the speed of convergence. If you assume this structure for the objective function, where g is some smooth convex function, and you assume a Lifshitz continuous gradient, which is given by this definition. Then the other assumption is the level set is compact. And the other one is that each upper bound function is strongly convex. Then,
How do you choose x0?
That's a good question. You can choose just any point that's within.
I mean, you will sweep and randomly choose some x0 such that you will find a compact set?
But then the point is that you need to prove that the set is compact. And then if you choose some point within the set, then it's fine.
So, sorry, are you talking about
Yeah, the
how to
initial
choose X
value.
zero
And yes,
when
the
you're running the algorithm.
Yes, the initial
You
value.
just
And I
need
think,
some
yeah,
feasible point.
feasible point. It just has to be feasible.
Okay.
Yeah. I mean, obviously, the final result would depend on where you start, of course. Yeah. But it would be like it would still converge to a local optimum or a station.
To the stationary point. Yeah.
But it could converge to a different station point.
Okay, so then provided that you have these two assumptions, A and B for the convergence, then BSUM takes at most C over epsilon iterations to find this epsilon optimal solution, and we can find the proofs on these two papers, 3 and 4. It's also not not proved in the signal processing paper, this one, but the proofs are here. I think 3 is the PhD thesis of the second author, and 4 is the science paper of the proofs. So it's quite nice. And then if you have some special structure, then BSUM takes at most O log C divided by epsilon to find this epsilon optimal solution. And it's in other two papers, 6 and 7. They also mentioned briefly that if you relax some of these part of the assumptions of B, for instance if B1 or B2 or B3, then you can have other speed of convergence. But this is an area that's not very that people have not checked much. I mean, there are some works on that, but still much is unknown on these convergence proofs. So then I'll give some brief ideas on the algorithms covered by the BSUM framework. The first one is the BCD, which is the famous BCD. And here I'm pointing to a reference, which is a very nice overview and state-of-the-art paper, I think it's from 2015 by Wright, on the whole story of BCD and the latest results. So the idea here for the BCD is that the upper bound function is the function itself. So it's also covered within the BSUM framework. The other one is the convex-concave procedure. And reference 9 is the famous convex-concave paper on neural networks. And here the idea is that you approximate only the function d2, which is also the minus, which is the concave function here that you are summing with g. Then you do some first order approximation of d2 and you optimize at each block this big function. So you can think of BSUM as also including the convex concave. And you can show this for many others, as I mentioned. The matrixation minimization, the non-matrix factorization, and in the paper, in the signal processing paper, they mention just a few. But in the science paper, they go into more details of each proof and how you do that and some other results. Then here I'll present some application of the framework on the machine learning. And the application is on the dictionary learning. So the idea is to use compressive sensing, which is basically the data signal is represented by a sparse linear combination of some signals in a given set, which we call dictionary. And then usually this dictionary should also be learned from the data. We can have this problem formulation that you are given some training signals. The dictionary learning task is to find this dictionary set, A, that can be sparsely represented by the signals in the training set. If you define in terms of matrices, for instance, Y, A, and X, then you can formulate the problem as this. You are trying to minimize over A and X some distance function that measures the goodness of your model, subject to A is within a constraint set, and also X is within a constraint set. So that's the general model. And if you choose some function, popular choice for the function, such as this one, we have this optimization problem that you're trying to minimize the Frobenius norm of y minus x, and then you have here some regularization term for the sparsity of the model. Then a popular approach to this is to use KSVD, and then you alternatively update A and X. But then what if now we replace this objective function within a quadratic upper bound that we saw before? And then we alternatively update A and X. Then here we have some results on image denoising problem. We see here that we are very close to the desired KSVD, But this is the proposed algorithm. This is KSVD. We are very close to the famous algorithm, but we are doing much fewer iterations. So we are still with the same result, but way faster. And this is also applied in signal processing, communication. You can find some, for instance, weighted MSE problems that are solved using this big idea of BSUM, and can find many others. In the paper, they just mention a few. And then here, I'll conclude the presentation. So I present this general framework for large-scale optimization. It has strong theoretical convergence guarantee and a big flexibility on choosing the index set and also choosing the upper bound function. We show that it covers well-known algorithms, so it's an umbrella framework, that all of these algorithms are within this idea. We allow for parallel or distributed computing platforms. And then we have more content on this paper that I didn't include here. So they have a bit more explanations about the covered algorithms, more applications in wireless communication, bioinformatics and signal processing, and then some nice extensions to stochastic optimization. If you have constraints coupling the constraint set, that is also very problematic. And you can use some game theoretical tools to solve this problem and to have a different view on this problem. So for these different constraints couplings, there are some very recent papers by December last year that are trying to solve that using combining BSUM and ADMM. They are quite nice. So, but here they are not covered because it's a 2016 paper. But still they give some hints on how to do that. It's from the same authors. So now I'd just like to mention some references. So one is the original paper. Two is the science paper that presents the BSUM framework. And here they have all the proofs and generalizations. For instance, they have, I think in section 5 of this paper, they present another way of using this cyclic rule, that you don't need to have n-1 single solution for the blocks. In fact, you don't need any kind of assumption on that if you use some selection rule, which is very interesting, because for many problems you cannot guarantee that the solution is unique. For instance, if you don't have a strongly convex function. Then the iteration and complexity analysis of the paper are proved on this very recent paper. Iteration and complex analysis, it was published on Math Programming. And then 4 is the PhD thesis of the second author, which is based on this work. It's quite nice, it has some proofs and other generalization, and many applications on wireless communication, signal processing, and machine learning. So it's also very recommended if you want to check more. And then on 5, you have the examples of upper bound functions. This is the ICML paper, but if you check on archive, the archive version has all the proofs. It has triple the pages of the ICML paper, so I recommend checking the archive version. Then they have another iteration analysis, but now using the BSUM and the ADMM framework. And this is the archive version of the paper. And then on this, there's another paper on iteration analysis for some cases, which was published in 2014. And then reference 8 is the overview of coordinate descent methods by Wright. And 9 is the classical convex concave procedure, if you want to check the first paper that was published on this idea, that popularized the idea. So with that, I would like to conclude the presentation, and thank you all for being here.
Thank you. So
Questions?
No question?
Maybe yeah, it's good to point out like some special cases of this, because I think this is a very big framework. Actually.
Yeah.
I think you mentioned some special cases. Actually, one is the BSUM, one is the normal BCD,
Yeah.
another one is this coordinate descent method, which was done in like 30, 40 years ago.
Yeah.
And then maybe some other special cases as well.
Yeah, so as a special case, we have this one, these two that Hadi mentioned. Then you have also the majorization minimization framework, which is also quite popular today. I mean, there are many papers by Palomar on this subject. So you can also fit majorization minimization within this idea, because in majorization minimization, what you just have is some special upper bound function, which is here, which is also covered by this.
Right.
This is one. Then you have others, for instance, this non-negative matrix factorization that is also included on this. So if you want to check some papers on these general BCD ideas and some convergence proofs that have nice properties, you can also check on this area on non-matrix factorization. For instance, we found some papers that you don't need to have n-1 block assumption on the single solution. You can have for some solutions n-2, n-3, and then the applications are on non-matrix factorization. So you can see that this is also included in the framework. Then you also have this expectation minimization, which is also very famous on machine learning. You can have here some more. Yeah. You can also have this proximal point algorithm, which is also quite similar to the idea of using the upper bound function with the proximal operator. And there are many ways to use the proximal operator. Then you also have this forward back splitting that is also very famous today. You just assume some different upper bound. The idea is just to select the good upper bound. For instance, if you have some upper bound that does not fulfill assumption A or part of assumption B, then you can get a better upper bound by just selecting the one that fits better your model. So in this way, it's quite general.
Yeah, exactly. And there are many more assumptions. There are different combinations of assumptions that lead you to different. Because I mean, this is a 30-year-old topic, I think.
Yeah.
And then in each, depending on how you select those assumptions, you can have good or bad, or I mean, strong or weak convergence results.
Yes. For instance, here they assume just quasi-convexity on the upper bound function, and you need a unique solution for all the blocks. But then in the other way, you can just assume that the set is compact, but in some ways to prove that this constraint that is compact is quite hard. So it's easier for you to just have a function that is quasi-convex. But this is just some way,
And then you said this algorithm reached to a stationary, not the optimal or
not the global, because
global
you cannot
optimal.
guarantee.
So even for the special cases like EM, because I recall that I was discussing with Hamid about the convergence of EM. I don't know whether you found any papers that says the EM actually converges to the global optimal or
No, not only the stationary part.
You can correct.
Yeah.
So I think all these special cases, you can just guarantee the.
You can guarantee the stationary
The
point,
stationary.
but depending on the specific problem, I mean, depending on the problem, you have different properties, right? And using these properties, you can prove maybe better convergence results. So it really depends. Here's proof for the general.
General cases. Yeah. But I think there are some, we came across some special cases actually. I think when you have two blocks.
Yeah, when you
I
have two
think
blocks,
there
then
was
you
some
can prove.
2001 paper that has actually they do the optimization of the two blocks only, and then they show convergence to the global optimum.
Yeah.
Then
I
you
think
need
there's a
some
very famous paper, right, by some Italian.
some Italian guys.
Yeah.
Yeah, exactly.
It's
So
over
there are
2000.
many special cases of this framework. This is the generic.
Yeah.
I mean the umbrella where everything else fits. And then if you like make the assumptions, I mean if you simplify the system model, right, as we say, if you think about two blocks, and then I think they need some assumptions on. So basically, I think F should be, the function should be strongly convex in each block.
And then that's
In
why
each of the
they
blocks.
require that the function has a unique solution. Because if it's strongly convex, you can guarantee that by, directly.
Yeah, exactly.
Because if it's
And then
strongly
you can
convex,
show
then you have only a
convergence.
unique solution.
Yeah. So there are many different combinations of assumptions, and then that each combination of these assumptions will give you like a different result, strong or weak, basically.
Yeah. Okay.
Yeah, but that's it's very generic. I mean, this comes up everywhere. I think people have used it for 30, 40 years without knowing that this is called BCD. Some
And it's
people use
usually
ordinate
for-
descent, some people say alternating optimization, many more.
Yeah. And many more, for example, using tensor decomposition, it's also quite popular.
Right, yeah, exactly. Exactly, yeah, so in a sense, this is a form of decomposition, actually. Yeah.
Can you comment on the set of indices?
Yeah.
So here
I mean, those convergence results are valid only for cyclic rule, or?
No, they prove here for the cyclic rule, but then they mention that for the randomized rule, it's just a slight variation of that. And it's proved in the PhD thesis, not here.
Can you define the randomized rule?
Yeah, so the randomized rule is at each iteration, you define initially some set of probabilities for all the blocks, right?
Okay.
And then at each iteration, you select some number and it goes to that block.
So some IID sampling
Yeah,
of the blocks
could
and
be.
then updating.
Yeah,
Yeah. Yeah, I think you define some a priori probability.
you define
for
some
taking each index.
probability and then you just, I mean, you can define the real
Yeah.
one.
Right. Right. Exactly. Yeah, but then the convergence is the same actually. It's still
quite,
convergence.
it's very
yeah.
similar.
Yeah.
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 It's not proved on this paper and also not in the science paper, it's in the PhD thesis.
Yeah. Yeah, I mean, I think most of these works are by the same group actually. So
Yeah.
this is, I think, Tom Lowe and his
Tom
students,
Lowe.
they've been doing that for like 10 years, maybe even more.
I think Tom was one of the first to prove some convergence results in the 90s.
Exactly, exactly, yeah. And then it was picked up by some of his students
Yeah.
actually. Yeah.
No more question? One thing, what would happen if we have somehow asynchronous updates? So if you update some coordinates several times without updating some other coordinates.
You can define that as another cyclic rule, and that's also included.
So it's like
That-
a randomized rule, but
It's like one, so as to say in cyclic rule 1, 2, 2, 2, 3, 1, 4.
Yeah, for
n.
instance, they have another, which they call the essentially cyclic rule, that
Okay.
you can define this set.
Yes.
And then as long as you update this every set within some large period of time, then it's guaranteed to converge.
What do you mean by large period of time? You mean
Larger than
sufficiently
the number of
large
blocks.
number of these
Larger than the number of
cycles?
blocks, just larger than that. For instance, if you have 5 blocks and you have like T10, and then I update block 1 from 1 to 3 and 2 from 2 to 4 to something, such that the union of all the iterations, it's covered in the set.
Okay,
So that's also proved. It's what they call the essentially cyclic rule.
okay.
And I think that's why they need those kind of like not special, like specific assumptions on the function actually.
Yeah,
So basically they assume that the function has to be strongly convex in each block.
Yeah, exactly. That was what
So
I
this
was
way, like, it doesn't
thinking.
matter like which kind of coordination, where do you start, which
Exactly, and where do you update?
and where do you
Yeah.
update, exactly.
as long as you update.
And if the minimizer is unique.
Yeah,
Exactly.
Again, it just doesn't matter how many updates you're doing in just one coordinate
Exactly.
or
Yeah.
not. Because
exactly.
you will
So-
get closer and closer.
Exactly.
yeah.
So
And also
everything
because the
depends on-
function
yeah.
has all points regular. in the
Yes.
set.
Exactly. Yeah. And then so the assumption is like basically like you make the assumption on the function and this upper bound and then the constraint set.
Yeah.
And then if you make those assumptions, then the order doesn't matter actually.
But how restrictive is that to have all the points regular?
Yeah, that's a good question. So they mention here, for instance, if you have this big framework here of functions, then they mention that it's easy to prove that all the points are regular. So in this big framework, it's easy to have many functions, but in other, it might be difficult.
Mm.
Yeah.
Yeah.
They don't dive much into that.
Mm.
Right.
But then you
Yeah.
have other ways of defining regular points. This is just one way. There's another one in non-smooth optimization that you use, I think it's called the Mangasarian Framovitz constraint qualification. That if you fulfill that, then the points are regular.
Yes.
Right.
But those
Yeah.
qualifications are usually very hard.
Yeah.
Yeah. Right. Yeah. But then sometimes this regular point is implied in the assumptions.
Yeah,
So I
it's
think
implied in the
yeah,
assumption.
Exactly.
It's already here.
Mm.
That each
If you have, I think if you have regularity and if you have convexity in each block, then it's implied that if the function itself is continuous and strongly convex in each block, or the upper bound is, and then the constraint set is compact in each block, so xi is compact, then this regularity is implied. I think you don't have to
Yeah,
worry about that.
exactly. Because we're just saying that if you have some point in the in the stack that converges somewhere,
Exactly.
then it's guaranteed to converge in the set because it's
Exactly.
compact. Then since it's
All the
strongly
sequences.
convex, it's unique.
Exactly.
So if you're going
Exactly.
towards the optimum of one direction, then you're going towards the peak. Not
Exactly.
optimal, but
Exactly.
stationary point.
Yeah.
Mm.
So then this is, I think, what we were trying to say, like when they were saying there are many different combinations of assumptions that give you
Yeah.
one result or another. Yeah. So that's why like this B sum is like kind of the umbrella that ties everything together. Yeah.
Yeah.
And then you can probably even do better actually. Yeah. I mean, if you have some special structure to the problem. So for instance, like if you know that your function f is strongly convex in each block, then you can do much better.
Mm.
Yeah. Then your convergence comes. You don't need B sum. You can
Yeah.
actually go to BCD actually.
Yeah.
The convergence result from BCD,
Mm.
and then you will show that this converges. So this is like one special case, so to speak. Another special case is like whenever you have some. So whenever you know that you have a coordinate, so the minimizer for each block is unique, then convergence follows in that case.
Yeah.
Yeah. So there are many more.
And that's the
Pockets.
classical way of using BCD.
Exactly. Exactly. And then this is, I think, the nice thing about this paper because like it's tying everything together.
Yeah. I think it's a good paper to have the intro into this big topic, but then if you
Yeah.
want to dive more into the details, I think you should go to the science paper or the PhD thesis.
Yeah.
The PhD thesis
Yeah,
is very informative. It's
Right.
very nice.
Yeah, I never read that actually.
Okay,
Okay.
cool. Some more? Okay, thank you.
Okay, thank you.
So